Today we're going to talk about a subject some of you may be familiar with, some may have heard a little bit about, and some already may be pretty involved with the subject, and that is chloropicrin soil fumigation in potato production. Let's get right into it. Sorry about that, wrong button. This is what we're talking about today: biodiversity and farming, chloropicrin soil fumigation, soil health, activity of chloropicrin in the soil, and modern agriculture. So, farming is a practice that alters soil microbiology and soil health right from the get-go. Repeatedly planting the same crop in a field over time selects for bacteria, fungi, weeds, organisms that can take advantage of the crop in which we're farming. Soil-borne disease, when it comes into that crop, further changes the micro community in the soil. And so as farmers, we have always farmed disease as much as we farmed the crop. And it's a battle between disease and production that we're always facing. So to battle against that, scientific knowledge, practical application of scientific knowledge, tries to give the edge to the crop and take it away from the disease. That's either pesticides we choose to use, agricultural chemicals we choose to use, or cultural practices that we choose in our business. Productive farmland is in short supply. Quality water supplies are becoming tighter. Familiar weather patterns are changing. It's getting tougher to farm. Food demand is always increasing. And the gap between the farm and the customer is widening. That means the folks that are buying your finished product understand less and less and less about what it takes to farm that crop. Of course, there are inequities in food supply around the globe. And really, society is looking for someone to step forward and say, we can navigate all this. We can produce food in a sustainable way into the future to feed the population as needed. And as we farm, we want to farm sustainably, like we mean to stay on the ground indefinitely, right? So we want to use practices that are beneficial to grow the crop and beneficial to the land we farm. Throw into this mix a product like chloropicrin. Chloropicrin is a soil fumigant. It's a fungicide and a nematicide. It's unique as an agricultural chemical in that it's been around for 90 plus years or so. There's a tremendous amount of scientific data on what chloropicrin suppresses in the soil, what it doesn't suppress in the soil. And it has a track record of suppressing disease, but it also has a track record of repopulating the soil with native beneficial microorganisms. It supports healthy crop roots, which leads to better water and nutrient use efficiency. So you plant crop into ground that's been treated with chloropicrin. You suppress disease, you get a healthier root system. That healthier root system is better able to utilize the nutrients and water that are applied. Leads to less crop stress, better crop quality, better crop yields. However, chloropicrin's a desperately misunderstood chemical. It's relatively new to potatoes. Roughly the last 10 years, we've been marketing chloropicrin into the potato crop. It's been used historically in higher value crops like strawberries, tomatoes, peppers. Fumigants are thought to sterilize the soil, cause irreversible harm to the soil that you're farming, and these ideas could not be further from the truth. Chloropicrin should be thought of as a selective agent, meaning that it certainly does not sterilize the soil. In fact, it continues to build soil populations of beneficial organisms and soil health over time. Chloropicrin is the active ingredient in the strike family of products. It's a list of organisms that chloropicrin suppresses, all the way from verticillium to common scab, rhizoctonia. A lot of these organisms play a negative role in potato production. Chloropicrin does not do a very good job of suppressing native beneficial organisms such as trichoderma. It's a soil saprophyte. It comes in, chews up organic matter, cycles nutrients, soil mycorrhizae, bacillus species, pseudomonas species that are also play a role in a saprophytic role in the soil, very beneficial organisms. So it's selective in that we can choose a rate that suppresses these organisms but leaves these organisms in place to repopulate after application. This is a field in Aroostook County, Maine from a few years ago, heavily infested with verticillium and early dye complex. This side of the field not treated, this side of the field treated. This farm actually got about 2.5 weeks more production out of the potato crop in the treated area compared to non-treated. This area putting on about 6,500 weights per day per acre. This field here, this side here, down to about 2 to 2,500 weights a day. Basically, when your crop gets to this stage with verticillium in it, you're farming the disease. You're growing that disease that repopulates the land and is there for the next time you farm the crop. This table here, somewhat involved, but we're going to walk through it. What it describes are 24 trials over 3 different seasons in Maine on russet Burbank potato. And these numbers represent an increase over the grower standard. In this case, there was no soil treatment at all. So putting chloropicrin in the ground increased tuber set per acre by somewhere close to 30,000 plus tubers. So by using chloropicrin and planting russet Burbank into that treated soil, able to increase tuber set by around 30,000 tubers per acre. These farms were able to move around 19,000 of that 30,000 into a marketable grade, which then resulted in an average over these 24 trials of a 9,400 weight increase over a non-treated control, which in these trials averaged out to about a 26% yield increase. No big surprise here. You suppress verticillium wilt. The main problem in most of these production areas, tonnage goes up. Yield increase changed over time based on weather conditions, production for that season, but there was a trend for increase over all 3 years. Certainly total yield is dependent on weather and management. So let's talk about soil health. TriCal Group, which I'm a part of, has been supporting soil health research for the last 5 or 6 years with a number of researchers across the United States. DNA technology has improved to the point where we can actually go in and identify microorganisms fairly easily in the soil and figure out what happens when you put a product like chloropicrin in the ground. How does that change that soil microbiology? We worked with Dr. Rosenzweig at Michigan State University for the last 4 years or so in studies. Dr. Richard Hogue in Quebec, single-year study. Ken Frost, we're just starting a long-term study with Ken for the next 6 to 7 years. And we've done or seen, others have done work in North America that we've not participated in, but really support the same conclusions that we've seen with Dr. Rosenzweig and Hogue, and we'll see, I believe, with Ken Frost. And that is chloropicrin is very effective at suppressing disease in the soil, verticillium, some nematodes like lesion nematode, acts as a selective agent like I already mentioned. We see a repopulation of beneficial organisms after application, within 2 weeks of application. They repopulate that soil and are around when that crop is growing to support crop growth. Not all fumigants behave similarly, right? So what I'm talking here today about is chloropicrin soil fumigation. Other fumigants select for different organisms in the soil. Research has helped us to understand that chloropicrin really triggers saprophytic growth. So those organisms in the soil, these soil saprophytes, which are fungi or bacteria, they feed on organic matter in the soil, cover crop residue. They turn over that residue and release nutrients. They're a critical part of a crop production system. You want good activity in the soil to help feed that crop. Saprophytes compete with plant pathogens. They actually outcompete those pathogens for resources, as well as just destroy those pathogens in the soil. They're also known to associate themselves with crop roots and help that crop be more healthy. They're, as I mentioned, a critical part of a healthy soil. So what happens in crop production? We want saprophytes in that system. We want a lot of soil biology activity, a lot of microbiology activity in the soil. So in a normal, healthy system, you have a healthy soil that feeds saprophytes. So you've got a system there where you're feeding those saprophytes organic matter. They're cycling nutrients. They're helping to suppress disease. They're leading to healthy crop production, which then leads to more saprophytes, and that system begins to turn. You see this cycle in the soil. We don't always see that in crop production, though, and we have a term for it. Most farms have tired soils, right? And we can identify those fields that we classify as tired. We just can't get them to produce the way they used to produce, and it doesn't seem like any practice we choose to do, cultural practice or chemical practice, helps improve crop production. The reason we end up with tired soils is because we're planting a similar crop over many cycles, that it's feeding disease. That disease is driving production levels down. Soil-borne disease builds up. We're using chemistries that impact the soil health, which then leads to low soil microbial activity. And you can measure that soil microbial activity through respiration. Those organisms breathe, and you can measure how well that soil is breathing, what the level of that soil activity is in the soil. As an ag industry response, traditionally what we talk about are soil additives. If you're going to combat a tired soil, you might add more humic acid to the soil. You might have some sort of bug in a jug, some microbe you're going to spray on the soil to try to relieve this tired condition. Or you might blame a micronutrient. We need more zinc, manganese, something there that's going to stimulate this soil and grow that crop. Culturally, what we're often asked to do is increase rotation length. So go from a 2-year rotation, a 3-year rotation, to a 4-year rotation or 5-year rotation to move away from that disease or find new ground. New ground's getting tighter, it's getting tougher to lengthen rotations. And so we're at sort of a loggerhead here where we're building tired soils because of use over time, and it's hard to find new ground, new productive ground to move into. I like to think of what's happening to our production land like this. If you imagine that big green bar being the first year of going into a new field, and that bar really is the potential yield for that field, right? So we've got high potential yield in a new field. We're adding short rotations into that field. We're adding susceptible varieties into that field. And we're adding chemistries into that field that can affect the beneficial microbes in that soil. Over time, that yield potential declines until we get to a point where we have this performance equilibrium. That's that tired soil point where we, no matter what we try to do, we can't get that yield back up to where it once was. Again, that happens because we've increased disease in that field. Those disease organisms, those microbes, are changing the soil biology in that soil. We see reduced soil respiration or soil activity in that soil. lower carbon turnover in that soil, less cycling of nutrients in that soil. That leads to lower yields, reduced root growth, where we have to apply more nutrients to try to push that crop later into the season, and limited soil buffering, meaning there's more stress in that system. That crop is less able to withstand the stresses during the season, which then again impacts yield and quality. All this we now term as soil health, right? How productive that soil is. Chloropicrin soil treatment, I think of it as a spark. We talked about how chloropicrin, we know it stimulates saprophytes. It's like a flame in that soil. Those saprophytes are going to begin to burn organic matter in that soil and turn those nutrients over, and they themselves will have an impact on how that plant performs. Chloropicrin suppresses disease, and it builds saprophyte growth, right? Populations. Those saprophytes, like I mentioned, utilize that organic matter as fuel, restarts the soil biology in that system, and it builds a healthy soil. So our soil begins to increase. Our yield in that soil begins to increase. We affect this tired soil syndrome, and we move it into a more productive soil system, where we have a maturing soil, better soil health, and we're moving more towards a sustainable system that's going to be productive over the long term. So we're not done with NOAA and all the other researchers we work with. We have a lot more questions about the growth of saprophytes in the soil, the beneficial microbes that return after application. That's all research we're continuing. Our next step is to figure out exactly how chloropicrin can build carbon reserves in the soil. A key concern now is the amount of carbon we have in the atmosphere. Can we use agriculture to store that carbon? And we believe with chloropicrin you can. If you have a system where you feed organic matter into production fields, whether with a cover crop or other cash crops, rotational crops, over a 1 to 3 year period, you apply chloropicrin, you drive that saprophyte growth, and you plant potatoes. Those potato crop production quality improves, and you repeat that cycle. Continue to repeat that cycle where you're feeding carbon in, selecting for saprophytes, producing a quality crop. Feeding the system with organic matter, basically what I just said, and stimulating saprophyte growth. You move carbon from a plant source into a microbial biomass, either alive or dead. Dead microbial biomass, it has sort of a gruesome term. It's called the necromass in the soil. That's a very stable form of carbon in the soil. And it can be used to actually trap carbon in the soil. So if you can increase that necromass by 10% in your soil, has dramatic impact on the amount of carbon that can be stored in that soil. Lastly, modern agriculture. How do we get to that? Modern agriculture uses available tools to improve crop production efficiency, produce more product per acre of land, while increasing the sustainability of that farmland. Chloropicrin builds healthy roots, which lessens the demand on inputs, fertilizer, water. Chloropicrin builds long-lasting beneficial soil microbe populations, which impact soil biology, soil chemistry, soil physics, soil properties in general, and it does not sterilize the soil. It can be used as a tool to store carbon in the soil, and chloropicrin should be considered a very sustainable part of a potato production system. With that, I'll say thank you. I ask you to come please visit our booth. We have these wonderful potato sizers to give away to anyone who shows up and wants to talk. And I think I'm going to step over here now and take questions if anybody has them. Thank you very much for your time.